Next, we have Mr. Tae Young from Shinhan Bank Digital Innovation Group. Mr. Tae Young has shared his insights in many conferences since 2015. He participated in creating POSCO ICT chatbot, Shinhan Bank's Soulmate chatbot, Soul Rich Road Advisor, AI OCR platform, and many more portfolio and engines. Today he will talk about the history of Vision. Please welcome him with a big hand.
So I can just use my microphone this way, right? So the topic, the history of vision is very much technical, and I will do my best in order to help you better understand about this technical aspect. And when you use vision at your workplace, you normally work it around image classification, image detection, and also object detection by applying many AI models. When you think of it, there's a deep learning models, and according to the SOTA standards, there are so many alignments like this. So if that is the case, we have to think about what kind of problems are there and how we've been addressing that issues and how we can develop further insight so that industries can introduce vision this way. So what's interesting here is that, yes, let's turn to the history of vision once again. This is the flow chart, which started from 2016 all the way up to 2018. There are so many neural architects, as you can see here. Now, most of the deep learning models are composed of the CNN backbone. So RCNN, faster RCNN, faster RCNN, and FPN. So many deep learning models are based on backbone. That's how the neural architecture is designed. Why? Why so many architects? And then the people do not abandon this backbone. This is because I think this is the focus over here. And there are so many certain papers, and the papers are very important in terms of a confidence level and also stability. That needs to be customized to the needs of industry, but that is not the case these days. There are so many papers around deep learning, and in the baseline, there's a pre-assumption about data, but the data actually generated are different to the assumption. So based on the papers, which became the reference, I think that becomes a very basic architecture that we have to think when we try to apply that vision. So there's a CNN backbone. Let me first turn to that. And then object detection is the second item. And then segmentation semantic, there is a neural network which is applied to the medical sector. So this is the order of my items. So let me first turn to CNN backbone. So GoogLeNet emergency is very important. Why? Why is it important? Because that was an experimental which made the depth of the network deeper, and it was related to optimization method. So deepening the network means what? Yes, the performance is improved. And as the network gets deeper, how does that happen? So the Google research team has conducted research on how to make the depth of the network deeper, and also which enable the realization of this deep net. And there's another set of papers related to this. So related to this Inception model, they could resolve many issues. And also when conducting training, and also when they did inference, they could also extract these elements that you can see from the slide. And the emergence of the Inception, I think, was a very much important element in GoogleNet. Does that sound very difficult to you? Are you following me? So what's important here is 5 by 5, 3 by 3. The convolution was happened in order to integrate all these different pillars. And Vision의 is also very interesting. So for the first time, convolution layer got deeper for the research. As you can see here, there are red convolution layer which was added continuously, and configuration itself was accumulated on top of each other. And there is a weakness because the number of parameters is large as the network gets deeper. But the VGGNet paper talks about what happens when network gets deeper. So they started to put more convolution layers, which made network deeper, and then they tried to get insight from it. And then ResNet also was emerged. And already it was emerged back in 2016 and 2017. As the network gets deeper, of course, the number of parameters increases, and also ERRORnet also increases at the same time. Then they thought about how they can address all these problems, and that's why deep residual learning concept emerged. This looks like this. So the purpose of function is, for example, hx minus x. So apart from the x, the rest was optimized. That was the perspective that they took. And then there was an identity shortcut connection here in order to optimize a very deep network and also in order to improve the accuracy in proportion to the depth of the network. So you need to know about all these facilities to decide which kind of backbone are you going to use, which kind of a neural network you're going to use, and how you're going to use optimization point. So you will be able to know about the handling point. Does that sound difficult to you? How does that sound to all of you? So the next slide is about ImageNet result. And of course, as the network gets deeper, performance will be improved, of course. And also error rate will go down. So what? You might ask. There are people say, so what? Why is that important? So is it really applied to the workplace? Is it really applied to the industry? And it's been done for good or bad? So what kind of improvement was made by applying all these to industries? And have you ever heard of the news that this technology was really, really beneficial to industry? Not for myself. I haven't really heard of it. I just heard that sort of paper is released and that was adopted and that was introduced. That was it. But for example, deep learning technology improved the
어떤 시스템의 획기적인 성능 개선
manufacturing of the semiconductors. I have never heard of it. How practical benefits were brought by this technology. So efficient network was emerged, which really changed the direction of the research. So what has been important was how to deepen the network and also how to improve the resolution of the image so that we can extract so many features from the image, all of which were the focus of the vision so far. And in order to really harmonize this, there was a paper released which was titled AutoNet. So many things have been changed. We do not have to do so many trainings. We do not have to make efforts in order to find so many parameters, thanks to AutoNet. So that was the paper which gave us a promising prospect of this vision. So we want to do more with less, and then we systematically analyze the model scaling this way. And then very basic is efficient network. And then thanks to that paper, we were sure that we can do that. We can address these issues. And we came to be really confident that we can reduce costs. So what's important here is to identify related work. What related work are there? For example, convolution net accuracy and convolution net efficiency, and also model scaling. Thanks to so many methodologies around this, there are ShuffleNet and also MobileNet appeared. So you, without properly understanding the history of vision, you might be feeling difficulty in understanding related papers while you are doing your work. So when it comes to MobileNet and SeparatNet, all these keywords came out when we thought about the future direction of the vision. As you can see from this model architecture, so many things are coming together and also separated from one another. There's a depth-wise separable convolution and squeeze and excitation are titles of the papers. And it is all about how to reduce the cost while improving the accuracy. So this became the center of the trend. And in the mobile version net 2, as is mentioned, depth-wise separable convolution started to appear here, mobile network version 2. Then what is that? This is very simple to understand. In a way, depth-wide convolution is about taking the features through the network so that we can use less memory resources while maximizing the performance. So I think you need to look at these papers, and the same can be said of a Senate, which is very interesting. The less net-based architecture stays the same. So without changing the basic foundation, how can we improve the accuracy? In the process, the paper entitled SNet came up and emerged. By combining this with the one that I mentioned earlier, we came to have the new neural architect. So you have to understand all about this so that you can apply the vision to the industry, and when you try to improve the neural architecture, you can actually apply all these technologies. And with cooperating with a neighbor, when I first came up with this kind of a model, I came up with the model which I applied Senate. And I told you about the CNN backbone-based network in the history of vision, how that was introduced to the industry, and what perspectives do we need. Let me now turn to object detection. So when we say object detection, it is composed of a one-stage detector and two-stage detector. What's that? It is about the vision proposal. So there are number 1 and number 2 classification. It is about whether you're going to do it all at the same time or two in a separate way. We have to think about which one is better and which one is less. So doing it in a 2 times, meaning that we can extract very small pixel-sized images. So doing it all at once, meaning that we can save a lot of time by roughly detecting the object from the image. So if that's the case, in the two-stage detector, there are concepts related to RCN. And what's important about RCNN is selective search-based paper were released, and also region of interest was extracted and retrieved, and there was a warping or expansion was conducted, and you can make the image in an identical size. And then CNN was put for the warped image, and then the forward image and feature vector image were extracted. About each class using the binary SVM, the total projection became possible. What's important is that we have to control the bounding box of the image. So there are limitations in RCNN. So in a total architecture, there's RCNN is separated from the SVM and regressor. So CNN is fixed. So as a result of the SVM and bounding box regression, we cannot update CNN, which make end-to-end impossible. So as we have to put ROI into CNN, then about 2,000 times of CNN computation is needed, meaning that it will take very long time, and which leads to the emergence of a fast CNN. What's different from the previous concept? And I would like to just skip through the slides in order to take you to the comparison table between the two concepts. So it's unfortunate that I only have 30 minutes to deliver my presentation. So there's a strength about the RCNN. You can use a CNN to categorize its class of the region. And the limitation is that the total framework cannot be processed from end to end. So it is difficult to find a global optimal solution. And also there's a strength about the image of the fast CNN. So everything can be put into one group and can be done all at once. But as a CPU-based processing is needed, still it is very slow. That's why it was led to fast CNN. So total frame can be learned by machine from end to end. There are still limitations. There are so many different components, and there's still limitations in terms of the time and also processing speed. As you can see from this architecture diagram, there's a regressor and SNM, and it can be exchanged between the two concepts. And also there's a cache area, and that can be changed to this. And also, although regression and softmax are used in 3 different areas here, but there's still another area that can be separated from here. So when you read papers about deep learning, you have to understand why this one is exchanged with another concept and why is it different to previous concept. You have to really understand when you try to read the papers about deep learning. And then that can be understood at the level of a code. Are you following me? It sounds that I'm the only one who are excited about this. I'm sure that this concept might be a bit difficult for you to understand. So there are many ways to measure the accuracy of object detection. This one is normalized case, but at the industry level, depends on the perspectives towards a perspective. Depends on the perspective towards a result. There are so many papers that you can refer to. To simply put, please refer to the slide. And there's a new concept about the average precision. So the precision and also the recall are inversely related with each other. And when we activate these two concepts, it depends on the insight that you try to get, and also depends on the decision that you will make about the output. There are so many different parameters, and also there are bounding box or overlapping area, which will determine the level of performance. And so cut-off threshold will be an element to determine the level of performance. So what it means is that whether you're tested positive and negative when it comes to COVID-19, this threshold is used to determine that. But sometimes even that the cell or that the virus can give you the result that you are tested positive. I think the precision and accuracy needs to be improved, which would take us to put more money. Right? And what is the one-stage detector? It is about doing number 1 and 2 all at the same time. So what did I tell you? It is fast, right? Because we are doing 2 all at the same time. And then YOLO, the channel or system, is what is best at. So YOLO, you only look once. It is a paper released by the student in the US, and it is a shame that the domestic researcher, domestic student, did not release any kind of this kind of paper. And yes, the image detection is done in real time. What does that mean? And once you look at the theory behind, there are so many different layers behind. And also this image is composed of SYS grid cell. And when it depends on the layers of the images input before. So it is a 7x7 grid cell image, and the length of image is this. And what's important here is that non-max suppression is used. So there's a bounding box drawn. So many bounding boxes will be drawn, and out of it, the bounding box with the highest probability will only be left. This is the important message behind YOLO. So non-max suppression is a function and formula used in order to leave the bounding box with the higher probability will be left. So ground truth and also non-max suppression needs to be matched with each other. And I better just speed up with my presentation because there's not enough time left. And there's a non-maximum suppression. There's only one instance should be applied to one bounding box. So this is a way how we're going to integrate all different kinds of bounding boxes together. And then this is how we started to overcome all the previous limitations. I know that my slides will be shared with you, so please download it for more details to get insight for your own. And there's an improvement made. And there's a feature pyramid network concept. And I'm sure you already know about this. All these things are coming together and also going out together in order to improve accuracy. So what's the feature pyramid network? It is about scale embedment for the object detection. So this is very important, the mechanism in order to identify the intrinsic feature of the original image. So this is a way to identify the object in the image, but it is very difficult to apply to the industry because it takes a long time. And without using multi-scale, it only uses the feature that is left toward the end. And this is one of the ways that we have used for single detector image. And this does not reuse already detected image features. And also low resolution and high resolution of the image featured and was extracted are combined with each other. So it can tell us about the loss values, but loss values are definitely reduced in this way. And this is bounding box prediction, which came from the YOLO version 3. I have about 100 slides prepared for this session. It is a shame that I only have 30 minutes. So what I'm trying to tell you is that the difference between one-stage detector and two-stage detectors, and what's the background of the emergence of the two concepts, and in order to improve the accuracy of the image detection. Two-stage detectors are used in order to improve the efficiency of the semiconductor manufacturing factories, but sometimes one-stage detector is used. It depends on the structure of the industries. So you have to apply the different kinds of detection methods. And when there's a heavy rain, the water will be splashed to the camera, for example. And then when there are the lights continuously moving and the systems are continuously moving, can you really trust the result of the system? Once you are in an autonomous vehicle, you cannot, right? So that's why data alignment is very important. But it is unfortunate that there's so many researches are being conducted, and segmentation is used in order to detect tumors in the medical industry. And there are two different ways. For example, semantic segmentation and instant segmentation. What's important here is that, for example, semantic segmentation considers people as a group, and instant segmentation considers the group as the group of individual people. And which one is preferred by the medical industry? Which one do you think, semantic segmentation or instant segmentation? Of course, instant segmentation, because it recognizes individual people, which led to the emergence of UNet. And it is used in order to improve the CNN, meaning that it requires high level of accuracy, right? And UNet refers to U-based network, as they are expanding a pathwork based on U. That's why it is called UNet. And basically, it is end-to-end method, fully convolutional network-based model. So this is composed of output, expanding path, and also U, which has neural architecture just befits the needs of the medical industry. As is mentioned, there's a FCN. And then I explained to you about fully convolution network for semantic segmentation to explain to you about the concept of FCN. Then what is that? It is about CNN-based model, which showed excellent performance in image detection. So in order to use network onto the special industry, we have to have the right value for input and also output, and we have to apply that method in order to improve the performance of the system. So that's why we came to have this series of different architects. And this is very important. There are path, contracting path and expanding path. What does it mean? For each different step, convolution path will be repeated over 2 times. But important thing is that padding is not used here. Why is that? And that's the feature of the RUNet. When padding is used, that would cause distortion of the image, that will lose the data related to the image, especially for medical images. That's one of the features of the RUNet. And then for each step of the expanding path, the constructing map and also upsampling will be used. That is what we call the skip architecture. Because of this part, I think we could further improve the accuracy when it comes to image detection. Because for the feature set, I think that can really look into a micro-size level. What it means by input is there are no limitations in terms of the size of the input image. So we can use the overall image, and then we can just put it into and divide them into smaller tiles. And this is how the unit has been evolving in the sector of segmentation, especially in the industry of medical sector. There were so many things I wanted to tell you, but it is unfortunate that I have a time constraint. So I have told you about all this, and if you have further things that you would like to know, please search my name along with the keyword deep learning. They will be able to get more knowledge and information. And please don't be hesitant to contact me. Thank you so much for paying attention. Thank you for your constructive presentation. We could see how much AI technology has been developed, as well as the future potential development of the AI technology.